Hello future pilots, let's start the next chapter of instrumentation, which is the directional gyro indicator, or often called the directional indicator. So let's see how a directional gyro indicator or a DGI looks like. So this is it, how it looks like. So there are three parts. You have to understand each function of those. The first one is the miniature aircraft. The function of the miniature aircraft, as you can see, the head of the miniature aircraft points the current heading at which the aircraft is flying. Next is the compass rose, which is just behind the miniature aircraft, and it looks like this. So as the aircraft turns, the compass rose also rotates. And next, the last one is the cage or adjustment knob. So what is the function of this? So the function is it resets and realigns the gyro by synchronizing it with the magnetic compass. So we can, with the help of this, we synchronize the gyro with the magnetic compass. We will read the reason afterwards. And also it redirects the gyro if it has toppled or it has drifted. Alright, so let's read this. The DGI is often called the directional indicator. It shows a steady directional reference to help pilots fly accurate headings and turns. So the function of the DGI, we can say that it is to help the pilots fly accurate headings and accurate turns. It doesn't have any magnetic path, so it's not like a compass that points to magnetic north. So let me explain you this. So in magnetic compass, what happens is that due to the magnetic properties, the needle of the compass points to the magnetic north. But in the case of a DGI, it doesn't work like this because DGI doesn't have any magnetic parts. And because it doesn't have any magnetic parts, the name itself, the directional gyro indicator, it works on gyroscopes, right? But here it is written that at the start of a flight, the DGI must be set or synchronized to match the magnetic compass. But what is the reason behind it that we have to synchronize the DGI with the magnetic compass? Because over time what happens is the gyroscopes, which is inside the DGI, it slowly drifts over time. And this is the reason we have to regularly check and reset the DGI. So let's read this. Because gyro instruments can slowly drift over time, pilots need to regularly check and reset the DGI. Alright. The DGI doesn't replace the compass but works alongside it because it gives a very stable and steady heading readout. So the function of the DGI is not to replace the compass but to work with it, because we know that the DGI must be synchronized with the magnetic compass in a very regular intervals, because the gyro instruments can slowly drift over time, right? Since it doesn't use magnets, the DGI isn't affected by magnetic errors or the Earth's magnetic field's verticals component. So as we know, the DGI doesn't have any magnetic parts, so obviously it doesn't get affected by the magnetic errors, right? So here it is written. So let us look at the construction and principle of operation of a DGI. The DGI uses a tight gyro with 2 degrees of freedom. So this DGI uses a tight gyro, and it has 2 degrees of freedom because it has two gimbals. This is the inner gimbal and this is the outer gimbal. The gyro rotor is mounted on an inner gimbal inside an outer gimbal. So this gyro rotor, you can see it is mounted on the inner gimbal, right? And this inner gimbal is mounted on the outer gimbal. The outer gimbal rotates around the vertical axis of the aircraft, allowing the aircraft to turn independently of the gyro rotor. So this outer gimbal can rotate 360 degrees about the vertical axis of the aircraft. Alright. The rotor spin axis is maintained in the yawing plane due to gyroscopic rigidity. So this is the rotor spin axis, and this is maintained in the yawing plane or the horizontal plane. It is due to the rigidity, gyroscopic rigidity. The instrument displays typically uses either a cylindrical scale with a lubber line or a vertical cart compass rose geared to the outer gimbal. So here it is the vertical cart compass rose geared to the outer gimbal. So as this outer gimbal rotates, this bearing also rotates, and which rotates this compass rose. The gyro rotor is spun by air jets powered through a pump that creates a partial vacuum, drawing cabin air to drive the rotor. So this rotor is spun by air jets. So how it happens is that there's a pump that creates a partial vacuum. There's a pressure change, right? There's a difference in pressure which causes air from outside to drive the rotor. So now I will explain you through this diagram. So this is how a DGI is constructed. So as you can see, this is the gyro rotor. This gyro rotor is mounted on the inner gimbal, you can see, and the bearing is mounted on the outer gimbal. The outer gimbal, this is the outer gimbal which can rotate 360 degrees. We have already read about this, around the aircraft's vertical axis. So we can say that the rotor axis, the inner gimbal and the outer gimbal are 90 degrees to each other. But you should know what happens during a turn. So when an aircraft turns, what happens is the instrument case, this instrument case around the vertical axis bearing of the outer gimbal, this is the bearing and this is the outer gimbal, it rotates. It turns around the vertical axis bearing of the outer gimbal. So, but you should also know that the spin axis of the gyro rotor remains fixed due to rigidity. So this spin axis of the gyro rotor remains fixed due to rigidity. So what happens when an aircraft turns? So when an aircraft turns, what happens is the instrument case also turns, which all this bearings also turns which rotates the outer gimbal, and as the outer gimbal rotates, you can see the bearings, it rotates the compass rose. As the compass rose rotates, what happens is you can see the aircraft, right? So this aircraft, this is a miniature aircraft which is fixed. This aircraft doesn't rotate, but the compass rose rotates. So as the aircraft turns, we can say the compass rose also rotates. As the compass rose, wherever it stops, the head of this miniature aircraft, wherever it is pointing at, that is the heading at which the aircraft is flying. So this is how a DGI displays the heading at which the aircraft is flying. Next, we're gonna study about the air jet and rotor alignment. The air jet spins the rotor and maintains its axis in the yawing plane of the aircraft. If the rotor axis topples but the aircraft stays level, the air jet applies force that precesses the gyro, realigning it back to the yawing plane. This self-correcting force is crucial for maintaining gyro stability. So we can say that there are two purposes of the air jet. The first purpose is to spin the rotor and to maintain its axis in the horizontal or the yawing plane of the aircraft. And the other purpose is that if the rotor axis has toppled or tilted, to realign it back to the yawing plane. But the question you should ask is that how it realigns it back to the yawing plane. So let me explain. Now look at this image. Rotor axis in yawing plane. So when the rotor axis is correctly aligned in the yawing plane or the horizontal plane, the air jet force, which is the X, directly spins the rotor efficiently. But what happens when the rotor axis is displayed? As you can see here, if the rotor axis topples, tilts out of the yawing plane, but the aircraft remains level, the airflow hits the rotor surface at an angle. You can see that the airflow hits the rotor at an angle. The angled flow produces two force components. One, you can see the Y1, one continuous spinning the gyro, and the Z1, but the other component acts of center. So we know that due to gyroscopic principles, any force applied to a spinning rotor causes a reaction force, which is called precession, which is 90 degrees ahead in the direction of the rotor spin. So the angled airflow component Z thus produces a precessional force that precesses the rotor axis back towards the original yawing plane alignment. So whenever the rotor axis is displayed, due to the angled flow, this Z component precesses the gyro back to its original yawing plane. So let us look at the function of caging device. So this is the caging device. So what is the function is that it resets and synchronizes the gyro with the magnetic compass. So we have already read that this DGI needs to be synchronized with the magnetic knot because it drifts over time. This gyro topples over time. It locks the rotor to prevent topple during synchronization or extreme maneuvers. So this caging device, it locks the gyro to prevent topple during synchronization or if there is any extreme maneuvers. It re-erects or resets the gyro after a topple. So whenever a gyro is toppled, through this caging device we can again re-erect the gyro or reset the gyro. So let's look at the DGCA limitations. So you should know that if the aircraft is subjected to excessive pitch and roll, the gyro will topple unless it is caged. So let's look at this. Maneuver limits without caging. So if it is not caged, what will happen is that the gyro will topple at plus minus 55 degrees roll or pitch for air driven DGI and plus minus 85 degrees for electrically driven DGI. So these two values you have to learn because it definitely comes in the exams. So what are the errors that affects the DGI? The first one is the gimbaling error. So this occurs when the aircraft banks or pitches. It causes relative motion between the inner and the outer gimbal, which results in small temporary heading errors during turns or attitude changes. But this error disappears once level flight is resumed. So let me explain. So the gyro rotor is inside two gimbals, right? So this two, what are the purpose of the two gimbals is to let it stay steady even if the aircraft moves. So when the plane tilts or banks, the outer gimbal moves with the aircraft. We have already studied in the construction and the principle of DGI. But the inner ring or the inner gimbal with the rotor tries to stay still and doesn't move as much because of the rigidity. So because one gimbal moves and the other doesn't, this relative movement causes the instrument to show a slight temporary mistake in the heading. So as the outer gimbal moves but the inner gimbals due to rigidity doesn't move, so due to this relative movement the instrument shows a temporary mistake in the heading. So it's like a gyro because the gyro gets confused when the plane tilts, but once, as you can see, that the error disappears once level flight is resumed. So when the once the plane is flying straight and level again, the error goes away. So this is gimbaling error. The next error is real wonder, or we can say random wonder. So this is due to the mechanical imperfections like friction, imbalance and wear specific to each instrument. So this is due to the mechanical imperfections. Alright. Next one is the apparent wonder. Apparent wonder occurs because of the earth is rotating and the aircraft moves across its surface. So as the earth is also rotating and the aircraft also moves across its surface, there's a error which it causes. So it is divided into two, earth rate and transport wonder, that we will study now. So what is earth rate? Because earth rotates at 15 degree per hour, a gyro fixed in space appears to change direction relative to the ground. So a gyro which is fixed in space, it appears to change direction relative to the ground. So let me explain you by this two example. So this is an aircraft that is parked in the northern hemisphere, which is pointing true geographic north, and also the spin axis of the gyroscope is also aligned in the same direction. And now if we attach a compass to the spin axis just like we did here, we will see that as the earth is rotating, we know that the earth is rotating at a 15 degrees per hour. So as the earth is rotating on its own axis, the gyro spin axis still remains in the same direction in the space. So we can see that the direction of the true north in relation to our gyro north appears to decrease in degrees, like you can see in the northern hemisphere. So we can say that there will be always a decrease in northern hemisphere, and for this reason the earth rate is designated negative like here, and the opposite in southern hemisphere, it is positive. So there is a formula of earth rate which is 15 into sine lat per hour. Why it is 15? Because earth rotates at 15 degrees per hour and into sine lat per hour. So the effect changes with latitude. So as we change the latitude, like in northern hemisphere and southern hemisphere, the effect changes. So when it is at equator, it is 0. The earth rate is 0 at the equator, because if we put the value of the latitude, which is 0 degrees in the equator, so 15 into 0, which will make it the earth rate 0, right? And which is maximum at the pole. The earth rate is maximum at the poles because we are going to put value 90 degrees in the sine. Sine 90 is 1. That means that the earth rate is 15 degrees at the poles. So it is maximum at the poles and least at the equator. So what is transport wonder? It occurs when aircraft move east or west across latitudes. The curvature of Earth makes the gyro heading appear to change. So let me explain. So when flying easterly or westerly, your gyro is moving across Earth's curved surface, right? It is moving across Earth's curved surface. So to an observer, it seems to change heading, as you can see. And this is what transport wonder is. It seems that the gyro's heading appears to change. So when flying easterly in the northern hemisphere, it produces negative drift. As it is written here, in northern hemisphere, in east, it produces a negative drift. So that is the reason it is negative here, over here. And in when moving westerly, it produces a positive drift. And this is the reason it is here plus, with a plus sign. And it is opposite in the southern hemisphere. So in east it is positive and in west it is negative. So you have to learn this. So what is the formula of transport wonder? The formula of transport wonder is easterly component of the ground speed divided by 60 into tan lat per hour. You have to learn this. And so we can say that the faster you travel or the further from the equator you are, the stronger the effect is of the transport wonder. Because if you are at the equator and tan 0 degrees is 0, so the transport wonder, there will be no effect. But as we go further from the equator, what happens is that the effect becomes more stronger. So let's now study about the latitude nut. So what is the function of latitude nut? The latitude nut is a small part in the DGI. This is the latitude nut that helps correct errors caused by the rotation of the earth. So it corrects the errors which are caused by the rotation of the earth, and it depends on which latitude you are in. Alright, so let's read this. A mechanical adjustment set for the flying latitude compensates the gyro for earth rate apparent wonder by producing real wonder in the opposite direction. So by the help of latitude nut, what it causes is that it produces a real wonder in the opposite direction. So it compensates the gyro for earth rate apparent wonder. It is only accurate for the set latitude. The latitude nut produces real wonder which counteracts apparent wonder caused by earth rate, but only for a specific set latitude. So this is the function of the latitude nut. So this is the end of the chapter. I hope you have understood everything. This notes you can get from the description itself. Thank you for watching.